All right, thank you. So I don't think I have any pictures of my study organisms or habitat, and after that last talk, I'm glad I don't, because I think I'd just be embarrassed. But I want to first acknowledge my co-authors. That includes Julian Martin with USGS, and then 2 grad students that were funded by the Sea Grant program, Brad Udell, who's here at UF, and Brittany Combs, who is at USF's College of Marine Science. And so I'm the one presenting today, but really those 2 students, Brad and Brittany, did a lot of the interesting work that I'll be presenting today. So I want to give them the credit. So natural resource management often entails competing objectives. So if you think about fisheries, you may want to try to maximize harvest or yield this year while still maintaining a sustainable stock for the long term for future harvest. Or in the case that I'll talk about today, try to reduce watercraft or boat strike mortality for marine mammals while also minimizing burdens and impacts to boaters and waterway users. So whether or not we realize it, we all use descriptive models in our everyday life to help us make decisions. But we think mathematical models in particular can be useful tools to guide management decisions. And we think they're useful because you can use them to generate predictions for various management options that you might be considering. You can also incorporate uncertainty around some of the input parameters and allow that to propagate around as uncertainty around your predictions. And if there's some data gaps for some of the inputs that are going into the model, you can do sensitivity analyses to just plug in some hypothetical scenarios and see how that influences your predictions. And also these models can be adaptive in that once you implement a management action, you can go out and observe the system's response to those actions and compare that against your predictions, and hopefully use that to improve your model and make better predictions and more informed decisions going forward. So the issue I'm talking about today is how watercraft-related mortality can be a significant threat for some marine mammal populations. So for example, this figure on the bottom left is a probability of manatee quasi-extinction under various levels of watercraft threat. And some primary management actions to try to reduce watercraft mortality has been the implementation of speed zones. So a lot of you may be familiar with speed zones for manatees in Florida, but also for North Atlantic right whales, they've implemented seasonal management areas where in certain areas and certain times of the year, ships 65 feet or greater are required to go 10 knots or less to protect right whales. Another management action are traffic separation schemes. So these might include no entry zones, or again, for the case of right whales, they've implemented these shipping lanes and put them in places where we expect lower right whale densities. Now, in order to try to optimize these protection zones, meaning, where should we put them and what should the speed limit be, and also to evaluate their effectiveness, we have to be able to quantify that risk of mortality. And this presents a problem because there's probably a lot of watercraft mortality that we don't observe, or even if we do recover a carcass and can determine that boat strike was the cause of death, we don't always necessarily know where or when the boat strike occurred. There we go. So what we did was develop this framework to help us to try to predict estimated number of watercraft deaths in a given area over a given time. And what we've done is kind of thought about all the different components that might go into the collision process. So one of the big parts of our work was developing kind of an analytical formula to allow us to estimate encounter rates between boats and marine mammals. And so this is influenced by things like the number of animals in the study area, as well as their size and speed. Similarly, the number of boats, as well as their size and speed in the study area. And we also note that boat speed might be something that could be controlled through management regulations. We also acknowledge that So we define an encounter as a boat and an animal being within some specified critical distance of each other at a given point in time. But we recognize that not all encounters necessarily result in a collision. So we can include things like if the animal is swimming beneath the surface, we can account for the probability that it's within striking depth of the boat. And also account for potentially the probability of avoidance, meaning that an animal or a boat might avoid each other actively kind of at the last minute to avoid a collision. And then similarly, not all collisions necessarily result in a death. So we can consider how the probability of death given a collision might vary as a function of boat speed or boat size or other factors. So with this framework, assuming you have inputs for all of these, we can estimate an expected number of watercraft deaths. And if we have an independent estimate of carcass recovery probability, we might be able to use observed carcass counts to help us validate this model using the observations against our predictions. So what we wanted to do with our work was kind of just illustrate some applications of this framework, and particularly estimating risk across space, time, and management scenarios. And we did that for Florida manatees in Collier County, and also for North Atlantic right whales in their southeast US seasonal management area in their winter calving grounds. And also with this framework, we demonstrate how you can account for parameter uncertainty. We do that through Monte Carlo simulations, and also did some sensitivity analyses where for some of those input parameters we didn't have good input data for, so we just evaluated sensitivity to those inputs. Now, in addition to just estimating risk, we also showed for manatees how you can use this framework to try to optimize the configuration of speed zones. And for right whales, tried to look at what effect that 10-knot speed regulation has had on trying to reduce number of expected deaths. So as I mentioned before, one of the important components we worked on was developing this analytical formula that allows us to estimate encounter rate between two moving objects. Really, you could apply it to any two moving objects, but we use obviously here for boat and animals. But basically, the encounter rate depends on that critical distance that I mentioned before, and that's based on animal and boat size, the size of the study area that you're looking at, the distance boat travels, boat and animal abundance, animal speed, and then boat speed. And again, noting that boat speed could be something that's regulated through management. So here's some examples for manatees in Collier County. As I mentioned, one of the big inputs are manatee abundance and boat abundance. And so up here is estimated manatee abundance that we modeled from aerial survey data using habitat covariates. So for example, season 1 and 2 on the left are warm water seasons, and basically manatees are more abundant over seagrass beds. And then over here are cold weather seasons where they're stacked up more in canals that might be looking for warm water. But what you notice is that abundance varies across season, and we did a similar thing for modeling boat abundance, also from aerial survey data, and also a little bit of variation across seasons there. But because abundance varies across season, that means the risk and also the optimal configuration of speed zones is going to vary across seasons. So that's something important to consider. What we also looked at was the, what's the effect of current protection zones relative to having no protection zones in place. So over here on the right panel is current speed zones in Collier County, with the black representing idle speed zones, the blue being slow speed, pink is 20 miles an hour, and then the yellow is no speed zones, and we assume that all boats go on average 30 miles an hour in those. So over on the left is our estimates of risk without any speed zones in place, and then in the middle is our estimate of risk with those current speed zones. And as you can see, those current speed zones reduce risk as opposed from compared to having no protection zones. And in fact, we were able to quantify that depending on some of our different assumptions, that the reduction was about 51 to 68% reduction. And we found that the results in particular were sensitive to what the probability of death given a collision, especially if it varies according to boat speed, and also probability that they actively avoid each other, again, if that varies with boat speed. So, identifying these as two important components for future research. We're also able to do some optimization. So what we did in this example was we wanted to keep perceived costs to boaters at the same level as the current protection zones and see if we were able to reduce risk for manatees. And we were able to do that. And this is what the optimum configuration looks. Again, it varies across the 4 seasons. We're also doing another optimization example where we kept risk at the same level as it is for current protection zones, but we were able to reduce the perceived cost to boaters. So right now, these are just kind of hypothetical scenarios. Some of the caveats, we're just using proxies that we developed for what boaters and waterway users perceive as costs. For example, that the slow and idle speed zones were weighted heavier because they're more restrictive. Also, if a speed zone was in a high traffic area, like in a boat channel, that might get higher weight as well. So I think in the future, it'd be good to work with, those stakeholders from the boating community and get their input on, how to quantify that cost. Also, as you can imagine, having a different speed zone configuration for each season would probably be something pretty difficult to implement and enforce from a management perspective. So again, in the future, hoping to work closely with managers and getting their input on what would be logistically feasible. And what's nice is you can formally incorporate some of those constraints into the optimization work. For right whales, I won't get too much into the results for the sake of time, but just give you an idea of some of the input parameters. So in each of these pairs of figures on the left is ship traffic density that we've been collecting through the AIS system. So you can see, high ship traffic off of Jacksonville here and some off of the Brunswick port as well. And then the right panel is estimates of right whale abundance that we also modeled from aerial survey data and habitat covariates. And you can see how that changes throughout a winter calving season as whales migrate in and out of the area. And then also we're also able to borrow work from other studies in the literature. So for example, this is the probability of death given a collision based on the speed that the boat was traveling at the time of collision. So some other researchers have developed that relationship, and so we're able to incorporate that into our framework. So in summary, we think this provides a flexible, transparent framework. We can account for spatial and temporal heterogeneity in abundance and how that translates to heterogeneity in risk. It allows us to evaluate different management alternatives. We can evaluate parametric uncertainty and also do sensitivity analyses to help prioritize future research. And also the framework can be easily updated as new data becomes available, or even if there's other components that you think could be added that are important to the collision process, those could be incorporated into the framework as well. And the nice thing is that because we're getting estimates of mortality from a specific threat, we can link these results to population models and recovery objectives. So through some of the sensitivity work we've done, we've identified some areas for future research. That includes obviously improving the estimates of abundance, as well as estimating abundance in other areas that I presented today. For manatees, estimating the probability of death given a collision, especially if that varies as a function of boat speed, will be important. Whether or not manatees and boaters actively avoid each other once they see or detect the other, and also how that varies with boat speed. And then, as I mentioned too, getting some stakeholder inputs to better quantify costs to boaters and waterway users, or the shipping industry in the case of right whales. So there's too many collaborators to list or mention here, but here's some of them. I do want to thank NOAA Fisheries, the Manatee Trust Fund, and Florida Sea Grant in particular for funding. Thank you.